Swayam Prabha. Digital India. Educated India.
Okay, so we will talk about number theory, which is the very essential field in mathematics, which is the very oldest field in mathematics and which is required for our cryptographic protocol, cryptographic primitives. So, let us start with the number theory. So, slide please. So, the number theory deals with the theory of numbers, and it is probably one of the oldest branches of mathematics. It is divided into several areas, including elementary number theory, analytic number theory, algebraic number theory. So, depending on the method we will use to prove some theorem, these are the areas it is defined. And here we will be talking about mostly on prime numbers. What are the prime numbers? What is a prime numbers? Because this prime numbers is required for many cryptographic scheme like RSA. So, we need to have a prime. So, what is a prime numbers? Then we talk about the GCD, which is greatest common divisor between two numbers, two integer a b, and then we talk about modulus operation, which is congruence operation basically, and then we talk about modulus inverse, which is required in RSA and some other cryptographic primitives, and then we talk about some number theory result like Fermat's Little theorem, Euler's theorem. We will discuss about Euler phi function, which is used in RSA and many other crypto system. So, let us start with the prime number. So, what is a prime number? Basically, it is an integer greater than 1 and which has basically no divisor. I mean, which has basically only two divisor, positive divisor 1 and itself. Okay. So, a number, a integer is called a prime if it has no divisor other than divisor means it should divide that number. Like if we have say 6 has two divisors 3 and 2. So, that means 2 divides 6 and 3 divides 6. So, that means since it has a divisor other than 6 other than itself and 1. So, that means 6 is not a prime, not a prime. But if we take 5 is basically 1 into 5. So, that means it has only two divisor, only two positive divisor, 1 and 5 itself, then it is called a prime. So, 5 is a prime number, is a prime number. So, and positive integer is called a prime if it has two divisor only. So, p, if p is called a prime, it has, if it has two divisor only 1 and p itself. No other integer a should exist, so that it divides p. So, this should not be, we should not find a such that this exists. So, this number is p is then called prime number. Okay. So, so it can be seen that 1 is not a prime, 1 we consider not a prime. So, prime number have very important role in cryptographic algorithm. So, we will see those slowly. So, now for any positive integer I, this is the fundamental theorem of arithmetic. So, any positive integer I, it is either a prime or it can be written as a product of prime. So, like if we have any positive integer, say 3 itself is a prime, 7 itself is a prime. Suppose you have 21 not a prime, but it can be written as product of two primes. Okay. Now, if we have 63, 63 can be written as in this form. Okay. Now, for example, if we have this 9975, so any integer I is either a prime or it can be written as any positive integer, it can be written as product of prime. So, this can be written as, we can easily verify 5 square into 7 into 19. So, that means any integer I is either a prime or it can be written as a prime factor. Dot dot dot, say there are say n p n e to the power n, where e I are greater than or equal to 0. This is a positive integer and p i's are all prime. Okay. So, this is the fundamental theorem of arithmetic. So, any integer I is either a prime or it can be written as product of prime factor like this. So, this if a integer is not a prime, then it is called a composite number, and then this is the first 10 primes 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. So, these are all prime numbers. So, these are first 10 primes, we can easily verify all these numbers are basically prime numbers. It is not having any common any divisor other than 1 and itself. Okay. So, if a number is not a prime number, it is called composite number. Okay. Now, we will talk about division. What do you mean by division of two numbers? Okay. Suppose we have two integers, let n and m be two integer then if we try to divide n by m. So, that means n can be written as q into m plus r, okay. And this r is basically called remainder, and this r is always lies between 0 less than r less than equal to m minus 1, because if r is greater than m, then q will be q plus 1, we will divide once more like this, and if r is 0, then basically n is equal to q into m. So, that means we say m divides n, we say this imply m divides n. So, that means m is a factor of n if r is equal to 0. This is the division rule, and what is q? Q is basically n by m. This is called lower ceiling. Lower ceiling means it is the least integer which is less than this. So, this is the flooring, lower floor, we have the upper floor. Okay. So, here is the division if we want to divide n by m. So, n is basically q into this, where all these are basically integer and r is the remainder, or it is sometimes called residue, and r must be non-negative, that is either positive or 0. If it is 0, then we say m divides n, and q quotient is basically n by m in the floor. This is basically the floor of integer floor. This is the integer part of this, but it is less than x. So, that means if it is say 2.6, floor means 2. Okay. 2.4 floor means also 2, but for 2.6 if we have upper ceiling then it is basically 3. So, if it is a upper ceiling, this is the notation basically. So, it is x bar is upper ceiling. So, like this. Okay. Now, suppose we want to divide 24 by 10. So, suppose n is equal to 24, m is equal to 10. So, we want to divide 24 by 10. So, 24 basically can be written as 2 into 10 plus 4. So, this is basically r, this is the remainder which is less than 10, which is greater than equal to 0, and this 2 is basically our q, which is basically lower ceiling of 24 by 10. So, this is basically 2. Okay. So, if we have any two integer, we can always have the this thing. So, now suppose when we say a divides b, suppose we have two integer a b, if you have two integer, let a and b be two integer, and we say a divides b if and only if b is basically some q into a. So, that means the remainder is 0, then we say a divides b. So, that means a is a factor of b. So, this is the division, and now we denote this by this form. Now, we will talk about greatest common divisor. So, greatest common divisor between a and b is denoted by m max, which is basically a divisor both a and b. It is a common divisor. So, it must divides both a and b, and any other divisor of a b. Suppose m n is the other divisor of a b, then it must divides, then m n must divides this greatest common divisor. Then we denote this by m max, which is basically greatest common divisor. So, basically we denote this by GCD, or the greatest common divisor, GCD of AB. If it is say C, that means C divides, it is a common divisor. So, C divides A and C divides B, and if any other divisor D, let D be any divisor, this, or this should true for all divisor of A B, divisor of A and B both. So, that means D divides A and D divides B, then D must divides C, and this must true for any other divisor D. So, this is basically, then C is a greatest common divisor of A B. Now, suppose we want to find the greatest common divisor of say 24, 32. Suppose A is 24. So, suppose you want to find 24 and 32 is how much you want to find this. So, A is 24, B is equal to 32. Now, what is the divisor of A? So, the divisor set of all divisor, set of 24 is basically plus minus 1 plus minus 2, these are all divisor of 24, plus minus 3 plus minus 4 and then plus minus 4, then plus minus 6, then plus minus 8, plus minus 12, plus minus 24. So, these are all divisor of 24. Now, this is the divisor set of 24. Now, let us take the divisor set of 32. So, this is basically plus minus 1, plus minus 2, plus minus 4, 6 is not a divisor of 32. So, plus minus 8, then plus minus 16 and then plus minus 32. So, these are the divisor of 32. Now, the common divisor means the intersection between these two set. So, the common divisor of 24 and 32 is basically the common integers, the intersection between these two sets. So, this is basically plus minus 1, this is common, plus minus 2 is common, then plus minus 4 is common and plus minus 8 is common. So, plus minus 2, plus minus 4, plus minus 8. Okay. So, these are the common divisor of this AB. Now, among these, who is the greatest common divisor? So, 8 is the GCD of this. So, 8 is the GCD of 24, 32. Okay. So, we can check that if you take any other divisor of any other common divisor of 24 and 32, like for example 4, then 4 must divides 8. So, that is the GCD of two number AB. It is a common divisor and it is the greatest common divisor. So, that means, if you take any other divisor, common divisor of AB, then that must divides this greatest common divisor. So, 2 is also divides 8. Okay. So, now we will talk about some result based on the greatest common divisor and then we will talk about how to find the greatest common divisor of two integer AB, that is called Euclid algorithm or Euclidean algorithm. So, some result we will discuss here. So, this is result or we can have a theorem form. So, GCD of AB is basically same as GCD of BA. This is quite obvious. I mean, we are just changing this thing. So, this is quite obvious, no need to go for the proof. Now, another theorem may be, so we can mark the number. GCD of AB is same as GCD of A, because AB could be negative also, but for divisor we are taking the greatest common divisor. So, this mod is, so if C is a divisor, then minus C is also a divisor. If C divides A, then minus C also divides minus A. So, this is also quite straightforward, we are not going to prove this. Okay, now theorem number 3 is basically GCD of A0 is basically A. Okay. And now we are going to prove a theorem which will give us the Euclid algorithm to find the greatest common divisor of two number AB. So, this theorem is telling, the statement of this theorem is, maybe this is 4. So, 1, 2, 3, 4, anyway this is theorem is telling GCD of AB is basically GCD of A plus KB comma B, where A, B, K are any integer. Okay, GCD of this. Now, how to prove this? Now, this is the proof of this theorem. Now, GCD of AB is same as GCD of this. Now, to prove this, if you can show that set of common divisor of AB is same as set of common divisor of these two, then we are done. So, basically if we can show that set of common divisor of AB is equal to set of, say they are same set, basically set of common divisor of A plus KB comma B. If we can prove that, then we are done, because then we can take the maximum of that set, I mean the GCD. So, we are going to prove this, the set of common divisor of AB is same as set of common divisor of A plus KB comma B. So, that means to prove this, what we need to show? We take a common divisor of AB. So, that will show is a common divisor of A plus KB. So, let us take that. Suppose C is a common divisor of A and B. Okay. So, that means C divides A and C divides B. So, C divides A means A should be written as XC and C divides B means B should be written as some YC. X, Y are two integer. Okay. Now, we will prove that C will divides both, C already divides B. Now, we have to show that C divides A plus KB. So, how to show this? So, A plus KB is basically what? A plus KB is basically A is basically XC plus KB, B is YC. So, KYC. So, this is basically X plus KYC. So, this is an integer, X plus KY is an integer. So, this is some alpha C, where alpha is an integer. So, this implies C divides X plus KB. Now, we already know C divides B. So, that means this implies C divides X plus KB and C divides B. So, that means C is a common divisor of this and this. So, one part is done. Now, the reverse. Now, we assume suppose C is a common divisor of this and this, and then we need to show C is also a common divisor of AB. So, that means C divides A. So, this is one part is completed. Now, the second part, suppose C divides C, suppose C is a common divisor of this and this. So, that means suppose C divides A plus KB and C divides B. Then we need to show C is also a common divisor of AB. So, that means we need to show that C divides A also. Okay. So, this means what? This means A plus KB must written as some x into C, some other integer x, and C divides B means B must be written as some integer y into C. Okay, now from here A is basically xc minus kb. Now k is basically yc, so xc minus kyc. So if you take c common, x minus ky c. So this is some integer alpha c, some integer alpha. So this means c divides a, done. So that means c is a common divisor of, this imply c is a common divisor of A and B. So that means set of common divisor of AB is same as set of common divisor of A plus KB comma B. So that set is same. So that means the greatest common divisor must be same. So this is the proof of this theorem. Okay. So from this theorem we can have a algorithm which is called extended, which is the Euclid algorithm, which is a method to find the greatest common divisor of AB. So this is coming from this, what is called this corollary of this theorem. So GCD of AB is basically GCD of A mod B comma B. Okay. See, this mod operation is basically what? So A is an integer, B is an integer. So if we divide A by B, then A mod B is basically the remainder. So like 24 can be written as, if A is 24 and B is 10 say, then 24 can be written as 2 into 10 plus 4. So that means 24 mod 10 is basically this remainder 4. So that means if we divide 24 by 10, then whatever is the remainder, this 4 is the basically A mod B. So that is that sense, A mod B. A mod B is basically, A is an integer, B is an integer. So if we divide A by B, the remainder will be the denoted by A mod B. We do have a modular operation, modular arithmetic, we will discuss in the next lecture maybe. So now this is the mod. So now how to prove this? We will just use the previous theorem we have discussed. So basically A mod B is basically R. So A is basically written as Q into B plus R, where Q is basically A by B. So this is basically R, this is basically A minus A by B into B. So this is of the form A plus KB, where K is equal to basically minus A by B, this integer. So now, so this GCD of, so this is we have seen. So GCD of, we know this result from the previous theorem, GCD of AB is basically GCD of A plus KB comma B. So A plus KB is basically A mod B. So GCD of A mod B comma B. So this is the proof of this result, and this result gives us the what is called Euclid algorithm to find the GCD of two numbers, which we discuss in the next class. Thank you.